Hi, this is Conrad Pereira. This is a presentation on the use of recursion in software development. We will cover the basics of recursion and then debugging, testing, and refactoring recursive code. This material is primarily based on MIT's OpenCourseWare. To begin, we will answer the question, what is recursion? Recursion is a process in which a function calls itself directly or indirectly. Recursive functions are defined in terms of base cases and recursive steps. The base case is the simplest, smallest instance of the problem, meaning the base case can't be reduced any further. The result can be computed instantly based on the input to the function call. Base cases typically correspond to emptiness. For example, this may mean an input of 0, an empty string, an empty list, and so on. The recursive step reduces a larger instance of the problem we're solving into one or more smaller instances that can be solved by additional recursive calls. And then it recombines the results of those subproblems to produce the solution to the original problem. We'll see a concrete example in a moment and identify the base case and recursive steps. As stated in MIT OpenCourseWare's section on recursion, recursion is not appropriate for every problem, but it is an important tool in your software development toolbox. Okay, now that we have covered the basics on recursion, I'll give you 5 seconds to answer. What type of problem encourages the use of recursion? First, obviously problems that can be naturally broken down into subproblems like the factorial function, Fibonacci, and so on encourage the use of recursion. These problems are solved with a recursive way of thinking. Next, an extension of problems that can be naturally broken down into subproblems. If we have a data structure that works well with recursion, such as a tree, graph, or linked list, we may definitely consider using recursive methods. Finally, if we have an algorithm such as sorting or searching, these problems can easily be naturally broken down into subproblems. What did you come up with? Let's solve a problem for computing the factorial of a given number. The factorial function says to multiply the whole numbers from our given number n down to 1. So if we call factorial with n equal to 4, the result would be 3 times 2 times 1, which is equal to 6. If we call factorial with n equal to 5, the result would be 4 times 3 times 2 times 1, which is equal to 24. Now that we understand what a factorial is, let's look at the code. We can do this both iteratively and recursively. In the iterative function, we are easily able to loop from 1 to n, multiplying fact by I each iteration. This results in the factorial being correctly computed. On the other hand, in the recursive function, we have no loop. The function will call itself until n is equal to 0. When factorial is called, this is a recursive step. Notice how it decomposes a larger problem into a smaller problem. N equal to 0 is the factorial function's base case. It cannot be reduced any further. Eventually, n will be equal to 0 and the functions will all return, and we will have successfully computed the factorial. This image further illustrates the recursive implementation of the factorial function. We can see if we call factorial with an input of 3, how it reduces until the base case, and then the function calls return, eventually producing the correct result, 6. I encourage you to walk through the recursive implementation's code and this image to solidify your understanding. Now that we know the basics of using recursion, can you guess why a software developer might decide to use or not use recursion over iterative methods? You can pause the video or take 5 seconds to answer, starting now. One reason may be that there's poor performance, meaning time and space complexity, with one of the implementations. Sometimes the recursive method is slower or takes up more space than the iterative method, or vice versa. Next, higher complexity, meaning that the code is more difficult to understand and is therefore harder to maintain and debug. Lastly, the method has a significant amount of repeated work. If we see duplicate code in multiple places, an alarm should go off. Maybe we should try something different. Did you come up with anything else? Alright, now let's delve deeper into the advantages and disadvantages of recursion. We will notice that many of the advantages can become disadvantages for some problems. Knowing the advantages and disadvantages of recursion is valuable. Otherwise, we may end up using it when it's not ideal. First, simplicity. graphs and trees. Many problems have elegant recursive solutions, whereas the iterative solution is much more complex. The nature of graphs and trees make recursion ideal for these data structures. Second, safe from bugs. Using immutable variables and immutable objects allows this. Also, as mentioned before, recursive code is much simpler for some problems we may be solving. Therefore, it may be easier to prevent bugs. Next, a small additional benefit for recursion is that what would be an infinite loop in an iterative implementation might become a Stack Overflow error in a recursive implementation. This means a buggy recursive program fails faster, which is good. Many problems are inherently recursive, but with some problems it is not applicable. More often than not, using iterative methods can easily solve the same problem. That's why it's important to consider the trade-offs between different implementations. The recursive implementation may have fewer lines of code, though sometimes we can have an iterative approach that may be simpler and have fewer lines of code. Again, this emphasizes the importance of knowing the trade-offs one is making when building software. Lastly, the performance of recursive functions in some cases may be great, whereas the iterative solution may be much simpler. A downside of recursion is that it may take more space and time than an iterative solution. The stack of recursive calls does actually consume memory temporarily, and it is limited in size, which may become a problem. If the efficiency is important, the time and space complexity of both the recursive and iterative implementation should be compared, and the better trade-off should be selected. These are some common issues with implementing recursion. The first one is the base case is missing entirely, or the problem needs more than one base case, but not all the base cases are covered. This may lead to a Stack Overflow error, or what would be an infinite loop in the iterative approach. We may also include unnecessary base cases in our implementation. This may lead to unintended results. The second most common is that the recursive step doesn't reduce to a smaller subproblem, so the recursion doesn't converge. Lastly, it's important to remember that the problem may not be inherently recursive. Our function may not be able to solve the problem for every case. We might have to use another technique. With that said, look for these when you're debugging. Testing code is important for preventing bugs from going into production. When testing recursive code, it is essential to include test cases that include values of boundaries. This is where many errors may occur. For instance, we cannot have a negative factorial, and our function should account for that, and return null or produce an error when there's a negative value. A simple approach to testing a function such as factorial may be to check the correct result and what the function actually returns for equality. Below we can see an example JUnit test case where we call factorial with -1, which we will say should return null. A great tip is to consider successful tests one that uncover an error. For example, this test shows that in our previous code for the recursive and iterative factorial functions, that we should determine how we want our code to handle negative inputs. Quick recap of what refactoring is. Refactoring is the process of changing a software system in such a way that it does not alter the external behavior of the code, yet it improves its internal structure. Refactoring code may allow us to make the software more maintainable. We will cover when to refactor code in regards to recursive and iterative functions. It's essential to note that costs with refactoring are much lower over time than without refactoring due to the maintenance cost of an unrefactored system being much higher. This trend can be seen in the graph below, and it really highlights why refactoring is such an important topic to bring into this conversation. We should also note that efficiency is independent of refactoring, meaning that it is not the main goal of refactoring. In refactoring, we begin with working code and do not change functionality or enhance the software. We are improving design that leads the code to be more maintainable and understandable. Recursion can simplify or further complicate our code. It is important to consider when we should refactor a recursive function that may potentially be overly complex. If there is a significant amount of redundant, inefficient, or unnecessary code, we should see if the iterative method will have fewer lines or has better understandability. In essence, when we improve or increase understandability and readability, structure and design, or maintainability, or on the other hand, when we reduce redundancy and unused code, inefficient or unnecessary algorithms, we should use the implementation. Use of recursion should only be done when it makes sense with the data structure we are using and the time and space constraints we have. And that covers recursion in software development. Here's a quick overview of what we covered and the major ideas and concepts to take away from this presentation. First, recursion is a process in which a function calls itself directly or indirectly. Recursive functions are defined in terms of base cases and recursive steps. We also looked at the benefits and disadvantages of recursion in development and when to refactor a recursive function or to use iterative methods. The trade-offs should be compared for different implementations. When refactoring code, it will allow us to make the software more maintainable. For example, if we find a simpler method of implementing a function, say the recursive technique had fewer lines of code and was easily understandable, then in the future it would be easier for other engineers to understand the code. Next, when testing our code, we want to make sure we can uncover as many errors as possible. We can find many of the errors at the boundaries. Lastly, don't forget the base case when using recursion. Otherwise, you may end up with a Stack Overflow error. That's it for this presentation on recursion and software development. Thanks for listening.